In this section, we will discuss about uh, construction of concentration cells and how to calculate EMF or cell potential or cell voltage for concentration cells, followed by corrosion and protection. In concentration cell, you'd have same two electrodes, same solution, but their concentrations are different. So here voltage is due to difference in concentrations. Like in this case, if you're looking at the reaction 1 and reaction 2, one is the reverse reaction of the other one. So if I consider that my first reaction, which I'm showing you here, nickel 2 plus 2 electron, that gives nickel, solid nickel. The first reaction, which is compartment, we're considering it compartment 1, nickel becomes nickel 2 plus 2 electron. So these are the two reactions we're looking at. If you look closely, one is the reverse reaction of the other one. So if the first one is the oxidation reaction, E0 oxidation, second one is the reduction reaction because the reverse of the first one. If I say that second one, reduction reaction, has the value of X, oxidation reaction must have identical value because the same reaction, only it is a reverse reaction. So it's going to be minus X. So keep that in mind. So standard cell potential is going to be 0. So E0 cell, that's why we wrote down here, E0 cell would be given by the sum of these two numbers is going to be 0. Next question that we have in mind, we have given these two concentrations. In one compartment, you have nickel dipped in 1.0 times 10 to the negative 3 molar solution. Another compartment, you have nickel dipped in nickel 2 plus solution, which could be nickel nitrate, nickel chloride, with 1 molar concentration. So one is much more concentrated solution of nickel than the other one. So the question is, which of these two reactions should represent the compartment with dilute solution of nickel? In concentration cell, it's very common that dilute one has to go up. So dilute concentration has to go up. On the other hand, the concentrated one has to go down. And eventually, both these concentrations will have to be the same because electrical voltage in concentration is due to concentration difference. So as you draw electricity out of that voltaic cell, what you'd notice is dilute solution is going to get concentrated, and concentrated ones would gradually get diluted, and finally they would have the same concentration, and then flow of electricity is going to stop. For now, let's come back to these two reactions. Nickel, the first reaction, nickel 2 plus, has to represent the dilute one because as the reaction happens in this manner, as nickel gets oxidized, you have increased concentration of nickel 2 plus. So if this compartment represents the dilute one, that means dilute means 1.0 times 10 to the negative 3 molar. That means this has to increase with time because that's how oxidation process is happening. Because each time it's being oxidized, concentration of nickel 2 plus is increased. So this has to be the diluted one. The reduction process has to be the concentrated one, 2.55. Because if you look at this reaction carefully, nickel 2 plus concentration, because of the second reaction, which is second compartment, is going down. Because as reaction happens, nickel 2 plus would be consumed and would be changed into nickel solid. So second compartment must represent the more concentrated one, where concentration has to drop with time. Okay, so now we identified which one would have the dilute solution and which compartment would have the concentrated solution. Based on that, can we say which one is anode and which one is cathode? Yes, we know that anode undergoes oxidation. So obviously the compartment 1 undergoes oxidation, and compartment 2 undergoes reduction, and compartment 1 has diluted solution, and compartment 2 has more concentrated solution. Let's go over problem number 70, and which is a very similar problem, similar to what I just discussed in last slide. In this problem, they are giving you concentration of Cl minus in two different compartments. In compartment 1, 0.0150, compartment 2, you have 2.55 molar. So obviously one dilute, the other one is more concentrated, and it has to be, because as I said, the electricity in this case is due to concentration difference, and that makes it a concentration cell. Now there are two reactions we are showing you. One is the reverse reaction of the other one, and that's the case in every concentration cell, as I mentioned before. Now, silver chloride solid in presence of an electron gives silver solid and chloride ion. So in this case, you have a chloride ion that goes in solution. As the first reaction happens, or reduction happens, what happens to the Cl minus concentration? That increases, because as you're getting more and more products, Cl minus concentration is going to increase. So this must represent, Cl minus represent in first reaction the diluted one. So let's write down here 0.0150 molar. So it has to be the diluted one, because with time, as we're drawing electricity, that Cl minus concentration would go up. In the second reaction, which is the reverse of the first one, Cl minus is being consumed as the reaction happens. So that concentration has to go down. So that means the second concentration must be the more concentrated one. So this second one is concentrated. So this would represent 2.55 molar. So make sure you understand that how we are assigning this based on the reaction and whether Cl minus gets increased or decreased. So here we identified Cl minus increases in compartment 1 and decreases in compartment 2. So in compartment 1, you can see here it's a reduction reaction. So red cat reduction happens at cathode. So compartment 1 would act as a cathode. Compartment 2 is an oxidation reaction. Remember oxidation reaction where electron is like one of the products. That means as the reaction goes on, electron is given off. So here that's why you see on the product side electron. And anox, so it has to be anode. So this end is anode, the other end is cathode. Because the other end, you have electron on the left hand side. That means electron is received by that half cell reaction. For question 70b, we are supposed to calculate standard cell voltage. Now, in a standard cell voltage, like for this reaction, each half reaction must have Cl minus concentration of 1 molar, because by definition, that's standard state. So basically, you're dealing with E0 oxidation plus E0 reduction for 1 molar concentration of Cl minus on each compartment. So basically, it's identical reaction. One is the reverse reaction of the other one. So if oxidation value is 0, is X, reduction value would be minus X. So if you think that reduction value is, let's go by reduction value is X. oxygen will be minus X, and that gives it equal to 0. Let me repeat this. For E0 cell, which represents standard cell voltage, concentration of Cl minus has to be 1 molar. In other words, you cannot have a concentration difference. It's a 1 molar concentration for both anodic compartment as well as cathodic compartment. So basically, one would be the reverse reaction of the other one, and they have equal and opposite value. When you add them together, it's going to be 0. Now let's calculate cell voltage for the concentration given, which is non-standard because one concentration is much more dilute than the other one, 0.0150 and 2.55. I already identified the first compartment has to have the lower concentration, because as the reaction goes on, if you think about the first reaction, as it goes on, Cl chloride reacts in presence of electron, gives silver and Cl minus. So that means as the first reaction happens in this direction, more and more Cl minus will form, and its concentration is going to increase. And that's what you expect in concentration cell. Lower concentration would increase. The second reaction, which is the reverse of the first reaction, must represent second compartment with higher concentration, because as second reaction goes on along the direction shown in this arrow by arrowhead, Cl minus will be consumed, so its concentration will go down. So second compartment must represent the higher concentration of Cl minus. So let's add them up to find out what is the overall reaction we get. So I'm going to use a different pen. Cl minus, you can see here, silver on one side cancels with silver on the other side. Silver chloride solid, just like in algebra. If once you have the same thing on right side and left side, you can cancel out or subtract. Each way you get the same thing. Now electron on the left, electron on the right, same number. So overall, by adding these two reactions, we get Cl minus 2.55 molar equals to Cl minus 0.0150 molar. So Q value will be given by, why we need the Q value I'll show you in a minute. Q value will be given by product divided by reactants, 0.0150 divided by 2.55, and that gives you 5.88 times 10 to the negative 3. Now, in order to get the cell voltage for part C, I need to use this expression that I'm going to write next. E cell, that's the non-standard. Why is non-standard? Because concentrations are not 1 molar. So E cell would be given by a standard value of cell voltage minus, since this is happening at 298 Kelvin, let me write down here 298 Kelvin, so I can apply this expression, simplified expression, 0.0592 over N and log of Q. Now, do I know the N value? Yes. If you look at the reaction, I already canceled out the electron. We have 1 electron. Let me circle those. So N equals to 1. So in this case, number of electrons being transferred from one half cell to the other is equal to 1. And we already know all the values. The standard cell voltage for a concentration cell is 0, because remember that's for 1 molar concentration for each half reaction, so it's basically the same reaction. 0.0592 over n, then log of 5.88 times 10 to the negative 3. Now that gives plus 0.132 volt. So this is the answer to this question. Now let's talk about corrosion and how electrochemistry can explain it. It is our common observation, if you have an iron rod sitting outside exposed to air and rain, after some time you'd find there'd be some kind of rust deposit on one side, and you'd have holes on the other side, like here you're seeing these. So that means that it would appear to you that iron must have gone from one side to the other side and made different types of compound. And that's indeed what was happening here. Now, you need a water droplet. So like say from rain, you got a water droplet, it's shown here. Iron, if you see that iron becomes Fe2 plus and gives off 2 electrons. And that 2 electrons, of course, it'd be used up. If you multiply this by 2, so you basically have 2 Fe2 plus 4 electron. Okay, this is Fe, this is Fe2 plus. So basically I'm trying to show you is this 4 electrons that will be given off by this reaction, anodic reaction, because it's oxidation, and that will be taken up at the cathode side where you have plenty of oxygen from atmosphere. So oxygen you have on this side, so oxygen in presence of H plus. H plus is always there in any in water droplet because of acid rain, or could be even in pure water has some H plus too. So that reaction will give you H2O, or just oxygen in presence of H2O and 4 moles of electron will be taken up, and it would give you 4 OH minus. Either way, you can explain this electron consumption on the other end, or electron receiving on the other end, where cathodic reaction happens. This OH minus reacts with Fe2 plus. Because remember, when Fe becomes Fe2 plus, it goes in water solution. This is rain droplet. Fe2 plus reacts with OH minus and first give a series of reactions of ferric hydroxide, and finally it becomes ferric oxide, which is a rust-colored deposit. So here we're showing you all these reactions in more details. So I already explained that to you. Iron in presence of oxygen and H2O, or you can even write down in terms of OH minus. It eventually gives you ferric oxide. And of course you have H plus. Now the question here is, will high or low H plus prevent rust formation? Answer is low H plus or high pH, because low H plus means high pH. Prevent rust formation. Now question is why? If you have low H plus, if you look at this reaction, if you have a smaller concentration of H plus, then obviously the reaction, cathodic reaction, would not be favored. If cathode doesn't accept electron, then electron would not be thrown out by anodic reaction, which gives off electron. So basically you need to multiply by 2 in order to understand the overall reaction. So that's how it prevents rust formation. So high pH is going to prevent or slow down rust formation. And indeed, when pH is greater than 9, there is no rust formation at all. Now, cathodic protection, often this term is used when you have a cathode that normally would undergo here we are showing you two other ways that one can protect metallic pipes by using magnesium as anode. That is going to force, so in other words, magnesium gets oxidized as Mg2 plus 2 electron, and that's going to force Fe2 plus to receive the electron, just like the last example, becoming Fe, and that's going to reduce the concentration of Fe2 plus. Since Fe2 plus is essential for rust formation, so that's going to be prevented. Similarly, iron pipes are often coated with zinc. Same idea. Zinc gets oxidized into zinc 2 plus 2 electron, and that forces Fe2 plus to receive electrons, becoming Fe. And this is how it prevents rust formation.